Okay, so today we're going to finish up with how functions are implemented in assembly in the Intel x86-64 System 5 API. And I'll also talk a little bit more about the compiler project, go over the actual project assignment. So hopefully you've started on this. It's due in a week. But remember, you have ample times to resubmit. And all the material is online already. Several of the functions are given to you. So before I begin, questions on what we covered last week with functions, or questions on anything else, questions on the project. Yeah.
Regarding the actual, not so much on the project itself, but more on the code gen reading. When it says given it in the assignment, do we just directly copy and paste, don't look too much into it, or?
You can use that code. So for instance, you mean the ones that says given to you, right?
Yes.
Yeah, you can directly take this code and use it for your compiler.
It should work?
Yes, it should work.
Okay. And as for the rest that are not given, is it just given what we have on the documentation, we just pull it from?
Yeah, given what you have in the documentation and in the lectures and in the homework. So for all of these, I've given you examples of what the output will look like. And taking what we learned about translation, where you have the parse tree for any input and the grammar which defines the names of each of these constructs, each of these listener functions is associated with one construct, and then you just kind of generate. You can think of this as a template for what enter function will generate, or think of this as an example of the template, and then you create a template for it and fill in the pieces from the parse tree, if that makes sense.
Yes, it does. On top of that, do we have to include the comments as well, or is that? No,
the comments, these are assembly comments. They don't have any computational meaning. So you can include them if you like. I just include them there to make it easier for me to debug and to illustrate it to you what the output looks like. It won't affect the test cases. Yeah, testing will only be on the output. So if you look at the code generation project, I've already given you some tests, and the way these work, if you open up one of these tests, it will run your program and compare the output. It won't compare the compiler output. It'll take the compiler output and compile it and run it. So this kind of comes back to this picture, where this is the program you're writing. The input of your program is IR. The output is assembly. And what makes the compiler a translator, or a correct translator, is that the inputs and outputs of the same program in simple IR have the same inputs and outputs as the translated assembly program that your generator produces. So the way I'm going to evaluate the correctness, or at least test the correctness, is to run the inputs and outputs on your generated assembly. And the way I'm going to do that is I'm just going to use, and it's in the test cases as well, I'm going to use, so this is what you're writing. You're writing a compiler here, but not for C, but for simple IR. And I'm going to use this rest of this toolchain here to actually build and run your assembly code on Eustace. So that's why that's why we have this calling convention. That's why we lay out memory the way we do, is because it ensures that your output assembly will match the conventions of the rest of the tool chain. So we'll be able to assemble, link, and load your program that you've produced from your compiler. So it'll fit into the rest of the tool chain. Does that make sense? Any other questions on that? Yeah.
I just want to verify in 6.1, you give the definition for interlocal variables. I think there was just a typo, and I just want to make sure I'm
There very well might be. 6.1 you said, right?
Yeah, in the first section before you go through the for loop, you say comments start from an offset of 2 times slightly from RVP, 1 for RVP, and then another to skip RVP, which will argument push. I'm assuming that's supposed to imply RVX.
Sorry, are you saying here?
Oh, no.
which paragraph? So I'm at 6.1.
Yeah, right there, that code snippet.
The, the code snippet. Oh, the comments. Let's see. So what's the typo, you think?
In that, those two comment lines there, you say you start from an offset of 2 times slightly.
Yeah.
One for RBP and then another for RBP, which will been pushed. Is that supposed to say RBX?
Oh, yes, to skip RBX. Yes, sorry. Yeah, it is. Thank you. So something I didn't, that you don't really have to worry about, and I didn't want to address I only sort of addressed it briefly, is that we also have to save certain registers that the caller might be using. This is part of the calling convention. Some registers are scratch registers that any function can use. Some are local to the function. They're like local variables to the function. And so I've given you code that will already save those registers for you. So this is really just part of the calling convention. You don't have to worry about it too much. I've given you code to do it. Yeah?
We had S and T registers, and then the difference was that the convention was that S registers would be preserved while T registers could, not be preserved. Is there anything like that in x86?
Yeah, I think the hardware doesn't specially define them, but the calling convention does.
Yeah, it's just like, is there a convention for like different kinds of registers like that?
There is, yeah. And yeah, but the convention is system dependent. So a Windows system may have a different convention from Unix system. So that's what that ABI, that's that System 5 calling convention. Yeah, it's all, yeah. And the hardware itself, the registers are actually, many of them are special purpose registers. So the A register is actually the accumulator register. And the C and D registers are for the division operation, as we'll see next time. Those are the only registers that can be used for division. So it's, so it's not as, I guess, clean or simple as the MIP register.
How many registers the NES had?
Either the Nintendo Entertainment, I don't know, probably like 4 or something, or 8. 6, okay. Average what I said. Yeah, not surprising. Registers are expensive to make. All right, they're more expensive than RAM, I guess. Okay, and I'm not sure if I made this clear last time, but if you look up, so yeah, here's a comparison of calling conventions. There's a link to calling conventions. Actually, I think I'm going to talk about this today. So we can see. So just to show you, yeah, these are the scratch registers as defined on different, Windows versus Unix, basically. They have different scratch and preserved registers, which makes things nice and confusing. They also have different parameter registers as well. So on Windows, you get 4 register parameters, but I don't know. And on 32-bit, there were no parameter registers. I don't know, just different designers, different decisions, different trade-offs in efficiency versus loss of registers. I don't know the history of these. These are standards. Standards are usually by committee. They're by agreement. So it folds in lots of different kind of stakeholder interests. Okay, other questions on what we covered so far? Yeah.
Maybe you can skip this if this is a little out of scope.
Okay.
I'm looking at the assembly for enter and I'm not understanding how do an add, and you do the literal 0
Yeah.
RSP. How does that work?
So this changes no state. So the reason that it's add 0, so 0 should be with whatever is subtracted from the stack. So as you'll see in a lot of the way I generate code for the compiler, I generate it in a way that makes me not have to have lots of different variations. So I don't want to write code in enter-end to say, okay, if I had local variables, then you add. Otherwise, don't do add. I want everything the same because it's just easier to generate. So when you, let's see, did I give you? Oh, I didn't give you enter-end. So when you run enter-end, you generate this. You generate the prologue of the function, which we talked about it a little last time. I'll talk about it more today. And I want it to be generated the same way every time, no matter whether there's no local variables or whether there are local variables. So I just always put the local variable offset when I generate the code. So that's why you'll see code that looks kind of pointless. But I, as the compiler writer, know that we'll take care of that in a later optimization phase. So take compiler construction. I always advertise classes, and now it's being offered in the fall, next fall. It should be offered in the fall. So if you're really like this class and you've taken programming languages in discrete 2, take compiler construction, and you'll learn more about how we take code that looks sort of inefficient or silly and actually make it automatically faster. So that way, us as the translator writers, we can make very simple translations, not having to worry about all the different possible corner cases, and then write later phases that will gradually make the code better. So yeah, this is just saying always add however many bytes or however many slots you added for, it's however many bytes you added for local variables, add it back to pop them from the stack frame. If I had zero local variables, then I'll add 0. Generating this is easier than checking every, for multiple cases and then generating different code for different cases. But no, that's a good, relevant question. All right, other questions? Yeah. One what?
Like the pop statement, you only have one.
For here?
Yeah, but then in the simple example, you have a bit of a two pop statement.
Which example? Oh, simple function. Oh, here.
Yeah, you have two pops in the SOR.
Yes, you're right. Let me double check the code to make sure I didn't miss something. Yeah, you're right. So it should pop RBX as well. Yeah, sorry, that's a mistake. Thank you for catching it. So this should also restore RBX. Thank you. So, okay, should be fixed now. Thank you for the catch. Anyone else have that issue or any problems when they... All right. Okay, other questions on homework assignment? Okay, let's go over the homework. Okay, so this is just to review drawing the stack frame for these functions. And so I said after running main and calling f, but before f returns. So basically the stack frame for f, if you included main, if you included f, both are fine. So main would have its stack frame first. Main stack frame, you didn't have to write all this, but main will have its own return address. It'll have its own parameters. It'll have two local variables, ret val and x. There's no parameters being passed, so there's nothing to worry about with parameters. Here's the stack frame for main. And then here's the stack frame for f. So it has a return address, has the old base pointer, which points to main's stack frame, and it will also have an old base pointer, but don't worry about that if you didn't do main's stack frame. An old base pointer and its local variables, which is just x. So as long as you had something like this, where you have the return address, the old base pointer, and x for f, then that's what I was looking for this. Questions on that stack frame? Yeah.
Could you build it as like two separate stacks?
Yeah, that's fine. That's fine. But they're all going to be like contiguous in memory, in real. But that's fine. Yeah. Yeah.
When you're doing the compiler code, like the moving, subtracting stuff, you need to subtract everything
For RBP.
Yeah.
So I've given you the code in the compiler for that, just because it's a little tricky to get that right, the offsets right. So I've given you code that creates the offsets. But yeah, this will be, so RBP will point here, and then this will be offset -8. Yeah. So in the actual compiler I have, I'm also saving RBX, which is what I forgot to show in enter end. But in your compiler, because of RBX, this will be -16. But if you just use the code I gave you, you'll have the right offsets. You'll have the right offsets for the code I gave you. And actually, now I'm realizing that, wait, enter end. Let me make sure I have the right code. Bless you. Yeah, it'll have the right offsets if you just use the enter local variables I gave you. So in practice, what the real stack frame will look like is it'll have the return address, it'll have the old RBP, and then it'll have RBX, and then the local variables will start here. So X will have -16 in the output of your actual generated code. So that's why in that full example, let's see if there's an example. Well, okay, it just says, yeah, so you just use the offset given there. Does that answer your question? Yeah, that's right. That's right. So here, I mean, it just depends on how you, like when you do the subtraction. So if you just push RBX here, if we push RBX, that's going to subtract 8 from the stack frame. Let me walk through what happens to the stack pointer and the register pointer, base pointer and the stack pointer. So I need numbers for these. So let's say this is 128, 120, 116, 108. When I come into this function, RSP will be 128. RSP will be here. And RBP will be somewhere pointing to the caller's stack frame. So when I perform the prologue of this function, the first thing I'm going to do is I'm going to push RBP, push the old RBP. So RBP is pointing somewhere higher. Let's say it's pointing to like 132, let's say. So the old RBP is up here. The first thing I'm going to do is I'm going to push RBP. This is the old RBP. And what's going to happen to the stack pointer after the push is it's going to, So let me start over. So what I mixed up is that RSP is pointing to the top element on the stack. So let's say this was this is the return address that was pushed by the calling function. So RSP is 128, and RBP is somewhere else. Let's say it's 140. It's pointing somewhere else higher on the stack. So the first thing I do when I'm running my function is I push RBP. So RBP is 140. So I push the old base pointer. And after the push, that's going to update RSP by subtracting 8 from it. So that's what push does. It copies the data that you asked it to copy and then subtracts the stack pointer. And then the next thing I'm going to do is I'm going to set the new base pointer. So I'm going to copy RSP to RBP. So that's going to update RBP to be 120. So RSP and RBP are both going to be pointing here. Next step is to push RBX. So pushing RBX is going to put whatever the value of RBX is in here. So that's going to save the caller's value of RBX, and then subtract 8 from the stack pointer. So RBP is still going to point here at the old base pointer, and RSP is going to be updated to be RBX, to pointing at where RBX was just pushed. And then finally, to allocate space for the locals, I'm going to subtract 24 from RSP. So that's going to be 1, 2, 3. Okay, my math is very bad. So 1, 2, 3. Is my math still bad? So it's going to subtract 24 from RSP. Man, I can't do it like basic math. So 112 minus 8 is 104, right? 104, oh yeah, sorry, I have to go another. So that's 2, that's 16 minus that, and then 24. So if I take RSP, subtract 24, it's going to put RSP here. So that's going to make 3 slots for these 3 variables, which were, well, it was supposed to be 3 variables, so X and Y, but there's only 2 here. So say there was another variable, X, Y, and Z. I'll double check these examples. I'll double check these examples again tonight. But so what this code is saying is subtract 24. So it's going to put RSP here, making 3 spaces for local variables. Oh, sorry. The reason for this, the reason that we had to subtract 24 when there's only 2 variables, again, has to do with the System 5 ABI. The stack has to be allocated at 16 byte, on 16 byte numbers. So the top of the stack always has to be divisible by 16. So there's another reason why I gave you the code for the prologue, part of the prologue, because the System 5 ABI is really annoying to deal with. So even though there's only 2 local variables, we had to subtract, in this case, subtract 24 instead of 16, because we had to add an extra slot to make sure RSP was 16 byte aligned. So anyway, I gave you the code for enter local variables, so you don't have to worry about this, and it should just work. But that's why. That's why in this case we have an extra slot here. It's not because there's an extra local variable. It's because of the System 5 x86-64 ABI requiring 16 byte alignment. But anyway, don't worry about that too much. Regardless, you could subtract any amount here, like 100 here, as long as it's more than 16, and your code would work correctly still. You just waste space. Okay, questions on this? I think we're sort of getting into today's lecture more, but questions? Yeah. Any other questions on this? Okay, so the move instruction that implements x equals 2 in the function above. So if you had, in this example, whatever offset you gave, whether it's -8 or -16 or whatever offset it was, the move instruction would take the constant 2 and move it into whatever that offset is from RBP. Let me draw that on another page. So you could have done this in a number of ways. So my compiler will first copy this to RAX and then move RAX into that offset from RBP. But you could also have just done an immediate store into that offset from RBP. Questions on number 2? Yeah.
In the context of function f, will it be immediate 2 or immediate 3?
Oh, sorry, immediate 3. Immediate 3. Sorry about that. Yeah, immediate 2. I was looking at main, got it wrong. It's immediate 3. Yeah, sorry about that. Yeah, it'd be immediate 3. Other questions on this? Yeah.
In my lab, the TA got -16 for the offset.
Yeah, so that was probably because he was including the RBX. He's probably including RBX like here. So for the homework, that doesn't matter. And I've given you the code that will compute the offsets, so you don't have to write that code for CodeGen. Just use the symbol table and the offsets that are computed for you in the code that I gave you. But yeah, he probably just included RBX here. I didn't really discuss that last time, so I didn't want to sort of require it for this when I didn't discuss that part of it yet. All right, other questions on the homework? Okay, let's get back into functions. So if you remember last time we had this example function called example variables. It declared 2 local variables, x and y, made some assignments, and then returned y. And this is what the assembly code looks like for setting up just the local variables. So we subtracted 16 from the stack to allocate 2 8-byte variables. We added that back at the end to restore the stack to where it was before we allocated the variables. Questions on that part? Just that part of the allocation? Okay, and this is what the assembly code will look like when we. Oh yeah, go ahead.
Before adding the 16 to the RSP, we must pop the local variables, right?
Say again. We should what?
Before we add the 16 to the RSP to restore it, we must pop the local variables, right?
No, adding 16 does pop them.
Oh.
So like subtracting from the stack pointer and pushing are equivalent. So pushing subtracts the stack pointer. So if you want to push without actually giving a value to push into memory, you can just subtract from the stack pointer.
So it's not like there won't be a memory leak or something like that.
No, they'll just be uninitialized data in the variable slots, which is why some C compilers, if you initialize a variable, declare it, but don't assign it and print it out, you'll get some value. It's a value you don't expect. And some compilers will actually warn you about uninitialized variable usage. So yeah, subtracting from the stack pointer is the same. It has the same effect as pushing to it. It has the same. Yeah, it just subtracts from the stack pointer. So adding to the stack pointer is how we pop. So instead of calling push twice here, to subtract 16 from it, we can say subtract 16 in one operation, and instead of popping twice, we can add 16. Okay, so this is what the assembly looks like for just for this example variables program. We first save the set the base pointer. Remember, the base pointer points to basically the beginning of the local variables in memory. It keeps track of the stack frame, and then we allocate space for local variables. So this is just like what we just showed in the homework. If our stack pointer is pointing here, then moving RSP to RBP will set the base pointer to also point to the same element on the stack. And then when I subtract 16, so this is subtracting 16, now my stack pointer points here. And my base pointer still points here at the beginning of my stack frame, or in the middle of my stack frame. Now basically it allows us to access the variables from a fixed offset. And I've subtracted 16 for my local variables x and y. And so in order to do assignment, which I think we covered last time, then we just use offsets from RBP in order to store values in memory associated with those variables. So if I want to store 1 into memory, I can either do an immediate load, or I can store 1, or immediate store, or store 1 into RAX, and then RAX into offset 8 from the RBP. So this is offset 8, this is offset negative 16 from RBP. So if I store the immediate value 1 into the offset 8 from RBP, then this memory location will have 1 in it. I can load the same way, so I can load from the offset negative 8 from RBP, which has 1 in it, and then store that value in offset negative 16 from RBP. So questions on this part of the function? The assembly version of our function? Yeah.
Is the return address always kind of taken care of by itself?
The return address is the old base pointer is not. We also have to do that. That's what I'll show next in the next part, saving them. But the return address is handled by the caller, and the base pointer the old base pointer will be handled by the callee. So this is just for variable allocation, just showing variable allocation. Okay, so return value by the convention, that's just set to RAX. And then we tear down the stack frame, and that will just pop these 2 elements from the stack and restore RSP to be where it was before we entered this function. And then return will get the return address and jump back to the caller. So questions on the variable allocation part of this, are the base pointer and variable allocation? Okay. So what your colleague was just asking is, what about the caller's base pointer? So a base pointer is a single register. We call in the middle of a function. We still need to be able to return to that caller and access its local variables. So the way we do that is we save RBP. We first save RBP before we start allocating stuff for our called function. So the question is, where does RBP point after the function returns, or it points to the old to the finished function's stack frame? So what we do to solve that is we first, before we start editing RBP, we save the old base pointer on the stack. And then at the end of our function, we restore it by popping whatever we pushed onto the stack back into RBP. So here's what the complete stack frame setup looks like for example variables. The first thing we do when we enter the function is we save the old functions, or the calling function's base pointer, save it onto the stack. And you can see that each step here is undoing the steps that we took in the beginning. So we save the old base pointer, we overwrite the base pointer with our new base pointer, so it's the current top of the stack frame, and then we allocate space for the locals by effectively pushing or subtracting from the stack frame. Once our function computation is done, we pop the local variables from the stack by adding to the stack, and then we restore the old base pointer by popping it from the stack. So here's what that'll look like on the stack. So we enter our function, the return address is already pushed by our caller, and RBP is set somewhere in the caller's memory. And after the return address is pushed, our SP is pointing to the current return address. So this is what the state of memory looks like when we branch to example variables, when we actually start executing example variables. Yeah? Call will push the return address for you. So call pushes the return address and then branches. And return pops the return address and branches to it. So this begins the stack frame for example variables if we have no parameters. This is I should say that the return address is part of the stack frame for it. But this is the, well, anyway, so this is the stack frame for example variables. I won't show the other stack frame. But this is the state of the stack frame when we enter example variables, when we actually branch to it. So the first thing that happens is we push the old RBP. So that's going to point to the same place that RBP is currently pointing when we enter this function. Next thing we do is we just, and that will, so that's a push, so that will update RSP to be the new top of the stack. Next instruction will copy the current stack pointer to RBP, so that will overwrite this RBP to be the current top of the stack. Question so far? Is that clear so far? Next instruction, subtract 16 from the stack pointer. So that's two 8-bit slots. So RSP minus 8 minus 16. RSP now points here on the stack. Yeah. Oh, because I have bad handwriting. That's supposed to be a B. It's supposed to be old base pointer, B. Sorry. So that's the state of the stack when we start actually running the instructions in our function. That's the state of the stack here. And then to reverse this, to clean up our stack, the callee managed stack, we add 16 to RSP. So that's going to change RSP back to here. Effectively making, and then we're going to pop RBP. So it's going to pop this value off the stack and set it to whatever, to set it to be RBP. So it's going to take this value off the stack and set it to RBP. And so that's going to make sure, or that's going to, what's going to, the consequence of that is now RBP will no longer give us access to our local variables at the same offsets. And then return. Return will, so yeah, they'll pop it off the stack, update the stack pointer, and then when we call return, that'll pop the address, the return address off the stack, restoring RSP to where it was before we made the function call, and branching to whatever that return address was. Questions on this? So these beginnings and ends of functions, they have names in the calling convention, and they're called the prologue and the epilogue. They're the sequence of instructions that you run before the actual function's code gets run. And so the function prologue looks like this. So we have an instruction that first saves the caller's base pointer, then sets the current function's base pointer to whatever the current top of the stack is, and then subtracts space by pushing or subtracting space from the stack pointer to allocate space for local variables. So that's the prologue. And the epilogue reverses this. It restores the stack pointer by popping from the stack pointer. Adding is equivalent to popping from the stack pointer. Then it restores the old base pointer by popping it off the stack, because remember we pushed it in the prologue. And then we return, and return pops the return address off the stack and branches to it. So that's the prologue and the epilogue. Okay, so here's a complete example of, let's do a complete example of calling example variables from main. So I'll draw, so main is also a function that gets called, so I'll draw its stack frame. It's got one local variable, so here's the stack frame for main. And when this function gets called, main will save its return address. So RBP will be here, RSP will be here, and this is the state of the stack when we first enter example variables. Questions on this? Questions on the setup? So this is just the stack frame for main, and then the beginning of the stack frame for example variables. Yeah.
So at any moment, RSP is always going to point to, like it's not pointing to the next. Like
Yeah.
If I put a variable, it's pointing at the one it just.
Yes, it's pointing. Yeah, it's pointing at the one.
Push, it moves, and then.
Yes, exactly. Yeah. So this is just the Intel architecture. Yeah, it points to the address of the last thing that was pushed. Think of it like the top of the stack. If you call peak
Not the space
on the stack.
above the top of
Right. Well, yeah. Well, it depends on what you mean by top of the stack. If you call peak on the stack, you'll get the top element. And if you call push, it'll push a new element, and then peak will be that new element. So you can think of like reading RSP as being like peak on the stack, if that helps, if that makes sense. Yeah, that's how I remember it, because I always forget this as well.
the you get nothing.
Right, yeah, exactly. So it's the top element on the stack is always RSP. Okay, so the call instruction pushes the return address onto the stack, which updates RSP to be pointing at the top of the stack, which now holds the return address. And then we branch into example variables. So here's the example. Here's the full example variables program. All it does is assign 1 to X and then just copy X to Y, returning Y. All right, so here's our prologue. This is the state of the stack before we start, right when we branch to example variables. This is the state of the stack before we execute the prologue. So remember, the call instruction has pushed the return address for us. So when we're in the example variables code, before we run the prologue, this is the state of the stack. RBP is here pushing to main's stack frame, and RSP here is on the top of the stack, which has the return address. Okay, let's execute the prologue. So the first thing we do is we push RBP. Does it help to have like actual numbers here, or do you prefer arrows? Who wants to see numbers as well? Arrows? Neither? All right, so I'll put numbers as well. Let's see if we can keep track of both. All right, so how much space am I going to need? I'll do both numbers and arrows. Let's see if my math is very bad, so. Please check my math, because I'm really bad at calculating. So just say, already making a mistake. So 6 minus this should be 248, and then 240, 232, 224, 216, 208, 200, 192. All right, so I think that's enough space, I hope. Okay, so this is what our stack looks like. Remember, it grows down in memory. So when you push, it subtracts from the stack pointer. Our old base pointer, RBP. So RBP is a register that literally has the address 248 as its setting, has that number. And the stack pointer is here. So this is the state of the memory before I call the prologue. Okay, so first thing that happens is we call push. We push RBP. RBP has value 248. So it literally pushes that memory address, the number of that memory address, onto the stack. So I'll just put a note here that that's the old RBP, just so we remember. Now, nothing else changes. That's all that, nothing else changes. So we push that onto the stack. That means we update RSP and then copy or store whatever RBP is into the current top of the stack. So let me do that one more time. This is the current stack before we start running the prologue. What does pop do, or what does push do? It updates RSP to be the next slot in memory, and then stores whatever value was asked, RBP, into memory. So 248 gets stored into memory. Okay, questions on that so far? So that was push RBP. So now here's the move instruction, move RSP, copies whatever the value of RSP is, which is this memory address 224, and it copies it into RBP. So now RBP and RSP will both equal 224 at this point. So both these registers have the value 224. Questions on that so far? And then finally for the prologue, we subtract 16 from RSP. So 224 minus 16 is 208. And so now all that instruction does is just change the value of the register 208. Nothing else happens in memory. It just changes this register value. Questions on that part of the prologue? Okay, so now we're into the actual body of our function. So this first one here, I'll just put a register for RAX down here to assign to X, and this code is given to you, the enter assign code is given to you. This will set RAX to be 1, and then it'll move whatever the value of RAX is into offset 8 from RBP. So here's RBP. I'll put the offsets on this side. This is -8, and this is -16. So if we want to access these memory locations relative to RBP, we can use this syntax to first subtract this offset, -8 from RBP, and then store or load from that memory location. Yeah?
Can you just set 1 equal to the offset of RBP?
Yes, you can. You can do that. You can do that. So my code does this because I want to use the same code to generate variable assignment and number assignment. But you could also just do an immediate load. So you can't do that for two. You can't do a load and a store in the same instruction. So you can do an immediate store, but you can't do, say, move -8 RBP to -16 RBP. Okay, so this instruction, the only state it changes is the value of RAX. It sets RAX to 1. And then this instruction takes the value of RAX, which is 1, and stores it in whatever memory location is given by RBP, which is 224, -8, which is 216. So this stores the number 1 into address 216. So now number 1 is here. Questions on that? Questions on that so far? And here we see a load from that address. I mean, you might also observe that you don't need to do a load here because RAX already has the value, but again, that's for optimization. So this move will take the value at address RBP, which is 224, -8, and that's this memory location, so it'll take this number and store it into RAX. RAX is already 1, so it's going to be no actual state change. And then here we're going to move 1 into the memory location given by RBP, -16. RBP is 224, so -16 is 208. So this move, the consequence of this move instruction is to set address 208 to number 1. And then finally we have a load from Y's memory location to RAX. No state change. Okay, questions on this so far? That's how assignment works. Okay, let's see the epilogue. The epilogue will add 16 to RSP because the stack goes downwards. This has the effect of popping 2 elements off the stack. So if RSP is 208, if I add 16 to it, I get 224. Then I pop RBP. What pop does is it first reads the value at the top of the stack, 248, and it copies it into whatever register is given. So this has the effect of taking RBP and setting it to be 248, which is the stack frame of our calling function, and then subtracting from RSP to restore the stack to where it was when we entered the function. And then finally we have a return call. Return pops the address off the stack, which copies return address, updating RSP to be the next lowest element on the stack, and then branches to that address, which is somewhere in the main function. And now we're back to where we started, right? So except for these state changes in the stack, this stack frame is preserved, and we have the old base pointer restored, the old stack pointer preserved, and so we're the exact same state that we were when we left main. Questions? Questions on this whole example? So hopefully that'll make tracing your code a little bit easier. And I'll show that should make tracing your code a little bit easier. If you actually draw off the stack frame, that will help. And I'll also show the RBX stuff. So once I get into the calling convention, I'll show you parameters and what RBX does, or what we have to do with RBX. But for now, I just want to make sure you understand base pointer and stack pointer and where local variables are accessed. Questions? Questions on this? Okay, so let's return to this calling convention. So we kind of covered this already, passing parameters. So when we involve parameters, this is what the stack frame looks like when we add parameters to the stack frame. So everything is basically the same. So here is the stack frame that we just saw. We have the return address, old base pointer, local variables. But for parameters, some parameters, the first 6 in our ABI, or application binary interface, those are passed via registers. But if there's more than 6 parameters, they're passed on the stack. The way this works is that the caller, before pushing the return address, is they'll push those remaining parameters onto the stack. So we have the parameters on the stack, then the return address, and the old base pointer. And this makes for a complete stack frame. Here's an example of what that looks like. I showed this one before, but here's the example again. So here's a function that has 8 parameters. So in our ABI, there's only 6 register parameters, so the first 6 will be stored in registers, and the remaining 2 will be pushed onto the stack. So here's what this stack looks like. We have the parameters pushed in reverse order. The remaining 2 parameters pushed in reverse order. That's why H is first and G is next. We have the return address, which is pushed by the caller, which is pushed by whoever calls this function, myfunc. Here's the old base pointer that gets pushed by the prologue, the local variables that get assigned by the prologue. And once the prologue is done, this is what the state of memory will look like for the currently called function. So you can see that from RBP, we can access local variables from negative offsets, and we can access parameters from positive offsets and the registers. So the code, let's see if I gave you, how much of this code I gave you. So I've given you, this gets a little tricky to read the manual for this, but the easiest approach that I recommend you do is, instead of trying to access these parameters via registers and the stack, the first thing you should do is just copy all of this data into local variables. So we'll basically just make local variables for these parameters and immediately copy this data into the local variable, so they'll all be accessed the same way on the stack. But okay, questions about this whole stack frame with parameters as well? So this top part here, this is what the caller pushes onto the stack. This bottom part, RBP and below, this is what the callee, the function being called, pushes onto the stack. Yeah.
For our implementation, we want to put all the parameters as local variables in the stack.
Yeah, so I recommend you do this. So you can implement it however you like, but I recommend doing it this way. So I've given you example code for what this looks like. You'll generate code that takes each of the parameter registers and copies it into its corresponding local variable location. So this is actually why in simple IR, when we talked about simple IR, the local variables include all of the parameter names as well. So if you think about like a C program, even though you've declared those variables next to the function name for the parameters, they're also local variables. The parameters are also local variables. So when you declare local variables, in simple IR, you declare all of the parameter names as well. So there'll be space for them on the stack. And so you don't have to do it this way, but it's easier to just, when you see the params construct, the first thing, what enter params will do is it'll just copy all of the parameters to their local variable locations. So this has one local variable that's not a parameter, x, and then the rest are local variables. And this copies each of the register parameters, A through F, to their corresponding local variable locations. And then it copies the stack passed parameters to their corresponding local variable locations. So here you can see that if when we have negative offsets from RBP, the x's are local variables. Positive offsets from RBP, that accesses the stack allocated parameters. So that's why here we have move 16 rather than negative 16. This is accessing the first stack allocated parameter. And this is accessing the second one. So it's 16 because offset 8 is the return address. So offset 16 is the first parameter pushed onto the stack. And because the System 5 ABI, the first 6 parameters are in registers. So that means the 7th parameter is here, the 8th parameter is here, 9th parameter is here, and so on. So it's pushed in reverse order by the caller. Okay, questions on the idea here, where the caller is pushing the remaining, 7 parameters, 7, 8, 9, etc., onto the stack, and then we can access those from a positive offset from RBP. Questions on that? Yeah.
We wouldn't have to worry about overriding the data whenever, I'm assuming whenever we call, it isn't like the call function.
This is the call. Once we're in this state and we have the RBP pointing here, we've set up the callee. Yeah.
And so, whenever we first initially enter in that function, all that it's there is just a return address.
That's right. That's right.
So say whenever we, go towards the bottom of the stack, the positive
Yeah.
offset, wouldn't we have to worry about not overriding data?
Yeah, for sure. Yeah. So the calling convention is just a convention. There's little to enforce that you use it correctly. So when you call a function, you're trusting that that function in your program is doing what it's supposed to do. Yeah.
So are you allowed to write to those positive offsets?
I mean, you're not supposed to, but the caller won't use that data anymore. So this is considered part of the callees. The function being called, this is considered part of its stack frame. So strictly speaking, you as the caller could overwrite this if you wanted.
Right.
Yeah, you could treat them as local variables. Yeah.
Yeah, I just so those, even if those are already, in the caller stack, you would, add those to the stack again.
Yeah, so this is kind of wasteful, right? Yeah.
Yeah, and then if you wanted to, put that, if the callee wanted to put that in stack, you'd have to copy that to its stack again. So it's 2 copies.
Yeah, so the way I've recommended you implement this is wasteful because you're going to copy this data onto the local variable stack down here. The reason I do that is because I want to be able to compute the offsets in the same function in local variables. So I don't want to have to go into enter params and then start updating the symbol table again. That's why. It was really just laziness to make a simpler compiler to write. So that's why I say you don't have to do it this way. You don't have to code this way because it is wasteful. It adds extra moves that you don't need these moves. You could just update the symbol table instead. For the register allocated ones, you could also leave them in registers as well and not even bother moving them. But then you'd have to keep track of which variables are in which registers, whether they're up to date with memory. And that's gets more complicated bookkeeping. So I made a much simpler scheme here where you just declare, I lost it, where you declare all local variables together at once. This will allocate all memory you need for all local variables. And then you say which ones are parameters, and this will do the copying from the ABIs, registers, and stack into the local variables. And then, yeah, we don't have to compute any more offsets. We don't have to worry about register versus stack. So that's why I say this is one way to do it.
Do you have to check if all of the ones listed in parameters are also listed in local variables, or can we just say that's undefined?
Yeah, I call it undefined paper. So the question was, do we check for this? No. So that's like type checking. So you also don't have to check whether a parameter is declared already. You'll just get a compiler. Your compiler will just break. You'll get a C++ error. You'll try to access an element that's not there. So yeah, I'm only going to test you on correct simple IR programs. Yeah, testing undefined behavior. This is the role of type checkers. Tests some classes of undefined behavior. So when you get a compiler error, but some of it is just left to the user. This is why you get like stack smashing attacks, null pointer errors, or undefined behavior. No one's checking it for you until you get to the hardware checks. But so as an ad for compiler construction, if you're interested in how that works, there are techniques for doing this automatically. You can see, we can see it in that class. So I tried to give you a simple, so it looks a little repetitive, but it's a much simpler scheme to implement for your compiler than trying to manage registers and memory and offsets into the parameter space versus offsets into local variables. So just follow this schema here to emit code when you enter params. When you see the enter params listener, generate code that will just copy all parameters to their local variable memory locations. And so it'll work just like an assignment. So if you have any, if you're curious about how the C++ code will look like for doing that, you can look at enter assign to help give you some hints on that. So enter assign does this. It generates a move from something, here in this case the register RAX, to whatever offset is assigned to that variable and RBP. So this is the code that will generate assignment-like stuff and parameter copying. Okay, other questions on parameter passing? So it's just a extension to this stack frame concept where the parameters are also stored on the stack frame. Yeah.
Probably a little topic, but since you mentioned that nobody kind of enforces that default and calling convention, is that how kind of attacks and malware can be written?
Yeah, for sure. Yeah, so the return address is supposed to be the return address to the caller, but the classic stack smashing attack, which has resulted in a huge amount of security exploits, if the developers aren't carefully checking that data being copied into local variables isn't overwriting, like say you have an array here, arrays extend in the positive direction in memory. So if XX or if YY is an array and I write to offset 1, well, okay, I write here. If I write to offset 2 or 3, I write to offset 2 here or 3 here. So if you're allowing your user to write to an array and you're not checking the bounds of that array, the user could potentially overwrite your return address. And then the return address will no longer be pointing to your calling function. And a very clever attacker can overwrite the return address as well as insert code, insert more data further up the stack, or further down the stack, I should say, that are like assembly or machine code instructions. So you could copy machine code instructions here, change the return address, and when the return happens, try to get a return address that is somewhere here in the stack. And so that way, when you branch to the stack here and the attacker has put machine code there, you'll be able to run arbitrary code. The attacker will be able to run arbitrary code from your program using your, if it's a server, then it's the server permissions. If it's root, then that's very bad. So yes, this is just a convention. There are techniques for enforcing this, like stack canaries, address space layout, randomization, control flow integrity. There are techniques for this. They should be covered in like maybe a security class or a malware class if you're interested, or let me know. I can point you to this. But yes, these are conventions. Okay, so let's get back here. All right, so let me show you an example of this program, and I think it's going to be outside. Okay, so on the right here I have my parameter example. It's main. It assigns x to 3 and then calls func passing x. And func will just take one parameter a and return that parameter a. So notice here I've declared local variables a and denoted that a is also a parameter. And I just return that value. So here's what the parameter passing looks like. So here's main. Here's my code for main. It has its prologue and its own, stack space allocation. But here's the relevant part. Here's the function call. So the function call will pass the parameter. So it's the first parameter, so it's passed via a register according to our application binary interface. And this is all just defined ahead of time. I've given you a vector in C++ that lists all these parameters. But the first parameter register is the RDI register. So the first thing this function call does is it sets RDI, the first parameter, to be x. So this is the offset for x. So it sets the value of x to the first parameter register. And then it calls the function. And that function will set up its own stack, tear it down, and then return, storing the return value into RAX. And once that's done, we'll restore the stack. So there's nothing was pushed onto the stack, so this doesn't actually change the state. And then save the return value in the retval parameter. So questions on this code, questions on the function call code. So notice that it doesn't involve at all setting up the rest of the stack frame for func. That's what the func code does. Func will do, has its own prologue and epilogue. But this is all that we need to do for function calls. We just need to set all the parameters, whether it's in registers or on the stack, issue the call, and then generate code that will restore the stack and save the return value. That's the function call. Okay, so this is the callee. This is the function being called. It has its prologue, which we talked about. It has its local variables. And then this is the code that will copy the parameter that was passed to its own local variable. So notice here the local variable was called A. There was space allocated for that local variable. And so this takes the first parameter, which by convention is passed in RDI, and saves it to the local variable for A. Questions on that? So this is all that needs to be done in order to save the parameter to its local variable slot. And then everything else is the same in this function. So once we have the parameter copied to a local variable location, the rest of the program can execute as we discussed before, just accessing its local variables. So that's why I have you do it this way, because when you hit the enter parameters listener, this is all you need to do, and then the rest of the function will work the same as if there were no parameters. So there's one larger example here that has 8 parameters. And so it works in just the same way. The caller will assign each of the local variables to will assign each of the local variables to a register. So here it's done in reverse order, but these are the parameters being passed into each parameter register, and then being pushed onto the stack for parameters 7 and 8. After the call, it restores the stack. So it pushed two parameters on the stack. It restores those, saves the return value. And in the callee, the function being called, these are all the moves from the parameter registers, and these are the moves from the stack allocated parameters. All right, so that's 1020. Take a look at the example code, walk through it, and hopefully it'll make it clear. All right, everyone, have a good day.
Thank you.